I mean, look, obviously everybody agrees that for sort of scientific advancement and technology development, reproducibility is absolutely critical. In particular, sort of in the early stages of a phenomena, especially as enigmatic as fusion or low-energy nuclear reactions, Leonard, skepticism is important, but I think that there's been sort of a decadal dismissal of cold fusion.
The Rational View is a weekly series hosted by me, Dr. Alan Scott, providing a rational, evidence-based perspective on important societal issues.
Produced by Soapbox Media.
The world needs evidence-based public policy now more than ever. Making the right decisions should not be partisan politics. Please help spread the Rational View by going to patron.podbean.com/The Rational View. Together, we can make a better future. Hello and welcome to another episode of The Rational View. In this episode, I'm revisiting the topic of cold fusion with an MIT-affiliated researcher who's looking into the case for cold fusion. As you may recall, my previous review found that there are many anomalous results in the field that point to the potential for new physical phenomena. Pons and Fleischmann's premature announcement of cold fusion in 1989 led to a fury of failed replication attempts and a lot of damaged egos. The way it was handled in the news, media, and in scientific circles left a lingering stigma which prevented further investigations through what I would call normal academic means. Only now, decades after the initial event, has it become possible for career scientists to start re-examining the evidence while still retaining their positions, albeit with the sanitized name of low-energy nuclear reactions instead of cold fusion. If you like what you're hearing, please press like on your podcast app and share the Rational View with your friends. Help me spread the word. Join my Facebook group, The Rational View, and I'd love to hear from you. Jonah Messenger is an interdisciplinary physicist, technologist, clean energy enthusiast, and eco-modernist. He's a doctoral candidate at the Cavendish Laboratory of Physics at the University of Cambridge and a researcher at MIT working on quantum coherent nuclear science in the U.S. Department of Energy ARPA-E Low Energy Nuclear Reaction Research Program. Jonah's research seeks to leverage quantum condensed matter physics to develop novel technologies that harness the energy of the nucleus. He's a non-resident senior energy analyst at the Breakthrough Institute, a consultant with the Anthropocene Institute, and a One Young World ambassador. A Udall scholar, Jonah earned his master's in energy and bachelor's in physics from the University of Illinois at Urbana-Champaign. Jonah, welcome to The Rational View.
Thanks so much for having me, Al. I'm a big fan.
Thank you so much. So you actually contacted me regarding your work after I published a series of podcasts investigating the claims of cold fusion supporters. So are you directly researching low-energy nuclear reactions for your PhD work right now?
Yeah, so it's not my PhD dissertation work. I'm working on sort of X-ray detectors for my dissertation at Cambridge. But just over a year ago, I went to my first sort of cold fusion conference, and I met with some of the researchers there, and was sort of still sort of in my learning phases, but was really sort of taken by some of the theoretical concepts that were being presented. And so I started to collaborate and work with these researchers at MIT, people like Peter Hagelstein, Florian Metzler, and others. And then at that same conference in Mountain View last August in 2022, the Department of Energy announced that the ARPA-E, so sort of the innovation arm of the Department of Energy, sort of akin to the DARPA program at the Defense Department, that they were going to actually start a research program. And so I was asked to help out in sort of applying for that program. We got the grant last March, and so I'm helping with isotopic analysis for that research effort.
Oh, very cool. So at what point in your career did you become interested in looking into cold fusion, and why did you decide to go to this conference?
It's a great question. It's a little bit funny, actually. So I was finishing up my bachelor's and master's at Illinois in Urbana-Champaign. And I sort of knew that a PhD was in my future, but I sort of decided to take some time in between my undergrad and master's work and my PhD work. And so I joined the Breakthrough Institute, which is an eco-modernist think tank based in Berkeley, California, and sort of we basically believe in technological solutions to environmental problems. And one of the board members there, Ross Kongenstein, was on a Google research project reinvestigating cold fusion, which I think lasted from like 2014, 2015 to 2019. And I was actually looking for a different article it is that he had wrote about climate change in IEEE. And then I came across this Nature Perspective article. I think the title was Revisiting the Cold Case of Cold Fusion. And so my initial reaction was, what in the world is Ross doing working on cold fusion? And so I read the paper and I talked to some of his co-authors and started to read some of the literature. I read a 2004 Department of Energy report prepared for the Department of Energy, sort of synthesizing some of the work that had happened in the prior decade, post the 1989 Fleischmann and Pons cold fusion situation. And there was about sort of 6 months of 6 or 7 months or so of sort of reading papers as best as I could with the time that I had, and sort of not being quite sure what to make of the field. It's some of it's quite enigmatic, and the sort of purported observables are disparate, and reproducibility is a challenge. It's really just sort of hard to make sense of the field and sort of tie together all these sort of purported anomalies that go well beyond sort of the conventional understanding of what sort of the claims of cold fusion are, which is that in an electrolysis cell you generate more heat than thermal power than electrical power input into the electrolysis cell. That's what I understood the claims of cold fusion to be. But I came to find many different claims, different observables, some far more compelling than excess heat. But it was still sort of just really hard to wrap my head around it all. And I knew that this cold fusion conference was coming up, so Breakthrough sent me, and there was a couple of presentations there that were scientifically super rigorous and very convincing. Particularly Eric Ziem. Eric Ziem had a really nice presentation on energetic alpha particle emission. That was for his thesis at the University of Illinois at Urbana-Champaign, actually, coincidentally. But then also sort of Nicola Galvanato, who's one of the people that I'm working with at MIT. He presented some work that based off of Peter Hagelstein's theoretical work. He's been working in this field for about 30 some odd years. And it was the first time where I sort of was able to process some of these. It was the first sort of theoretical framework that, while not finished, it was the first time that I could sort of start to see how some of these seemingly impossible problems that face cold fusion from a theoretical basis might actually be not so impossible. And so that was sort of what really, that coupled with a series of experimental reports that were, there was no light bulb moment, but there were just a few drop to the floor moments where I was sort of reading the paper and, thinking that shouldn't be possible.
So, I mean, the Nature Perspectives article, 2019, I guess it was, I mean, they didn't come out saying that cold fusion is real.
Correct.
They basically weren't able to find anything reproducible. Is that, can you maybe summarize what their findings were? So we can get a kind of a grounding.
Yeah, so they ran several experiments. They ran electrolysis experiments. They ran glow discharge experiments. They ran, with a particle accelerator, where they would accelerate particles into metal hydrides. And you're correct. They didn't find any evidence for cold fusion. And their sort of Nature Perspective article was, in a sense, sort of explaining why they were doing this research in the first place. And reproducibility is not a new problem to this field. But I think my perspective on the importance of reproducibility, and especially at what stage of the scientific phenomena reproducibility. I mean, look, obviously everybody agrees that for sort of scientific advancement and technology development, reproducibility is absolutely critical. But in particular, sort of in the early stages of a phenomena, especially as enigmatic as fusion or low energy nuclear reactions, LENR, I think it's a mistake to sort of be overly dismissive or skepticism is important, but I think that there's been sort of a decadal dismissal of cold fusion, in part based on grounds of lack of reproducibility, but as my colleague at MIT, Dr. Florian Metzler, as he's pointed out, the emergence of the transistor actually was a quite anomalous phenomena at first, before it was sort of conclusively proven and demonstrated by Bell Labs in 1947. But before that, there were, I think the first patent for effectively a transistor was like 1926. And there's some really juicy quotes from like Wolfgang Pauli, where he says something like, one shouldn't work on semiconductors. It's a messy business, and who knows if they're real or not. So I think there are some historical precedents for sort of phenomena where it's hard to reproduce, but in part there are hidden variables that are hard to control, and I think we see that a lot in this field.
It's true, but I mean, we also know that there's a lot of things that are pseudoscience and that are not real that also have the same characteristics of irreproducibility and researchers fooling themselves rather than actually making good measurements. So some care and skepticism is necessary, but I think you're right that there are this field has been kind of stigmatized over the years after the Pons and Fleischmann announcement, and so people have steered away from it. And mainstream academia, for example, it's kind of an anathema to take this on. Did you not get the memo that this was a career stifling move?
Yeah, it's funny. A mentor of mine who's sort of got a very technical background, when I told him that I was sort of looking into this field and I thought that there might actually be some there, we got on a Zoom call, and the first thing he said was, Jonah, I hear you're flirting dangerously close with cold fusion. So, sure. But I think, I think that there are experimental reports over the decades from dozens of different research groups using different experimental setups that all show, not all show, but some of them show, sort of compelling nuclear anomalies and different kinds of data as well. So I think there's some sort of converging experimental evidence that there's something there. And then I think that there are also some good theoretical motivations as well, which is historically, I think, been, one of the, certainly one of the sort of main reasons for skepticism. And I try and say as much as possible, sort of, I very much understand the skepticism. I think the skepticism is good and healthy. And certainly for a plasma physicist, I mean, this must make no sense. And so I can understand that there are some sort of pedagogical barriers for sure. But I think ultimately, I think we should all sort of work on what captures our interest and what we think is sort of scientifically interesting. And then I think now, quite frankly, I think it helps that I can now sort of point to the fact that it's not just me or sort of the people that go to the Cold Fusion conference, but Biden's principal fusion advisor, Dr. Scott Su, was, and Dr. Evelyn Wang, who's the director of RPE, they, sort of were sufficiently convinced that there was enough there that it merited a research program. And so, I think even when I talk to people who are quite skeptical, there are certainly some people who will be sort of, not very, collegial or nice, but I think that there's a lot of people who, while they may be skeptical are totally fine to sort of hear me give a pitch or sort of just to talk about why I think there's something there that merits my time.
Yeah, do you think that there's still pressure in academic circles at least, to stay away from cold fusion? I know it was kind of a tongue-in-cheek message from your supervisor, but do you think there is pressure to stay away?
Sure. I mean, I hesitate in answering this question because I can take it both ways. So I think on the one hand, there is still a lot of sort of cultural there's sort of a lot of cultural dynamics here that still very much treat cold fusion or LENR or whatever you want to call it as sort of a pseudoscience and not serious and, could hurt the reputation of an institution or these types of things. But I think there's a lot of young scientists in particular who, maybe didn't come around or didn't come up with that sort of backdrop. And I also think, and this is something that I think will be, and this is somewhat of a prediction, but I think, if you look at the history of the transistor, there's some of this too, where sort of there are these anomalous effects, and there's this sort of emergent field that is somewhat taboo. But then sort of in parallel, there are other scientific domains, other fields that sort of end up converging to the same point, right? So for the transistor, it was sort of electron band theory, single crystal growth, these types of things. And I think that in the case of LENR, I read papers in Nature Physics that I go, I think that might be quite relevant. So for example, there was this Nature Physics paper by Jonah et al., and they show that by coherently exciting iron 57 nuclei, they get excited and they'll emit characteristic gamma emissions, X-rays. But by coherently exciting at first 2 and then 5 and 10 and then 20 on iron 57 nuclei in an ensemble, the decay of those excited iron 57 nuclei is accelerated. So, for example, just to sort of put some rough numbers, this is these are just made up numbers, but if you have an iron 57 nuclei and you excite it, let's say it would decay, the decay rate would be once per second. And then if you excite 10 of them together, you would classically expect that the decay rate of the ensemble is just 10 per second, just 10 times 1. But actually, there is sort of very uncontroversial physics where the decay rate can be accelerated above that, up to n squared, so up to 100 per second. And so this Nature Physics paper showed a 15-fold acceleration of the decay rate going from an ensemble of 2 to 20. And I think that sort of coherent nuclear science arena will end up sort of actually kind of converging quite nicely, I think, with an explanation for LENR.
Interesting. So is that is that similar to lasing in photonics, where you have stimulated emission of photons from excited atoms or molecules?
Yeah, that's the right idea. I think the math is going to be somewhat different. So I don't think that it's I don't think a stimulated emission. I don't think this is sort of like stimulated emission, but it's sort of like accelerated spontaneous emission. And so this field is referred to as superradiance, where if you coherently excite a radiating species, as the ensemble gets larger, the decay rate accelerates.
So by coherently exciting a nucleus, you're pumping energy into it. Is that effectively changing the energy level of the nucleus?
I think maybe it's worth, certainly for the listeners, to sort of back up for a second and just say a quick bit about fusion and explain, maybe part of why cold fusion is so hard to sort of grapple with. Sort of bare bones, nuclei are protons and neutrons held together, and the reason why they don't break up because they have all these positive charges and there's this electromagnetic repulsion is because of the strong nuclear force. So residual force from the strong force that acts at short distances to bind these protons and neutrons, these nucleons together. And some nuclei are held together more tightly than others, sort of bound more compactly. Particularly iron and nickel are very, very tightly bound. And I assume this will be sort of well known for most of your listeners, but just in case for some it isn't. And so for lighter nuclei, if you bring them together and they fuse, the mass of the resulting nucleus will be ever so slightly smaller than the sum of the masses of the two reacting nuclei. And that missing mass gets converted to pure energy, and that's why people want to do fusion.
And that's using Einstein's equation of E equals mc squared, where m is the mass, E is the energy, and c is the speed of light, which is a huge number. And you square that huge number, multiply it by the mass difference, and that's the energy that is released in fusion.
Exactly right. So that small little mass gets multiplied by 2 speeds of light, lots of energy. Now, the problem is, of course, that if you want to bring two nuclei together, they're both positively charged, like charges repel. And so there's this electrostatic repulsion. This Coulomb barrier is what we call it. And so in conventional sort of plasma fusion science, the name of the game is get these nuclei together, pump a bunch of kinetic energy into the system. That kinetic energy can sort of overcome or allow push back against the Coulomb repulsion, get the nuclei close enough together, and then the strong nuclear force can do the rest. And so, I mean, there's I guess the other thing to say is that the products from these fusion reactions are very well understood. Plasma physicists have been working on this for decades. Some of these fusion reactions have only sort of one pathway, and there's only one set of products, and some of them have a few different pathways. But we know what the products are. We know what the different pathways are. We know how likely each of those pathways are. And we know what the energies of these products should be. And cold fusion, sort of tautologically, is hard to. I think there's sort of three problems, right? We've already touched on one, the reproducibility of the experiments. The second one is that sort of even in the name, it tautologically doesn't make sense, right? Cold fusion. No, you need to get it hot. You need to supply lots of kinetic energy so that you can
collide these particles together.
Exactly. And then the third one is that the cold fusion experiments. So again, most people think that cold fusion has no radiation emission characteristics, and that's at least regardless of what you think of the literature, the claims in the cold fusion community are not that. There are claims of neutron emission, gammas, charged particles, etc. But the claimed products don't line up with conventional fusion pathways. Okay, those are our three essential issues.
That was one of the main criticisms of Pons and Fleischmann's original announcement, is that the plasma physicists said, well, if it was making that much energy, they'd have been killed by the radiation. So obviously it's not real. So, it was poo-pooed and shut down relatively quickly because of that discrepancy.
For sure. And look, again, I can't emphasize this enough. From a plasma physicist's perspective, I completely understand that reaction. And I mean, it's funny, I don't really know exactly what I would have thought of cold fusion exactly before I started reading the literature, but that would probably have been, that along with sort of the cold nature of cold fusion, that probably would have been my reaction too. But one of the sort of fundamental assumptions that you make on a plasma is that interacting nuclei, right? Those two nuclei that have the Coulomb repulsion are completely independent from other interacting nuclei in the plasma, and that makes sense. There's no coupling. There's those two reactions aren't talking to each other. Mm-hmm. But in a metal, that's not necessarily the case, and certainly muon catalyzed fusion is an example of that's actually where the original sort of usage of the term cold fusion comes from, and that's completely conventional physics. It was, I think, developed in the 50s. I want to say at Los Alamos, and that's basically where you generate a muon, you fire it at a target, and then the muon kicks out the electron. But because it's so much heavier, it brings the hydrogen isotope nuclei closer together, and you can tunnel through the Coulomb barrier, and you get some fusion reactions.
And that's a lot of quantum mechanics for the listeners. A muon is basically a really heavy electron, and it changes the quantum interactions between these nuclei so they can snuggle up really close.
Exactly, and there's a variety of reasons why that wasn't pursued commercially. Although there's some really interesting folks at NK Labs. That would be actually another good folks to talk to, and they're working on they think they have a new approach to muon catalyzed fusion. But in any event, but in that case, you see the conventional fusion products, right? So that's effectively sort of like a low energy nuclear reaction that is that doesn't sort of have anomalous fusion reaction products. Mm-hmm. And in some of the early theoretical papers that sort of I wrote in a piece for the Breakthrough Institute called "Fusion Runs Hot and Cold." I wrote about this, and sort of that ostensibly will preclude the possibility of cold fusion, even though actually, if you read those papers, that's not quite what they say. What they actually say is that the fusion rate that they calculate in the most optimistic scenarios is essentially unobservable, right? So you'd have to wait way too long to see a spontaneous, I mean, in principle, in a bottle of hydrogen gas, there could be a possibility of a fusion reaction. You just have to wait, 10 to the 60 years or something crazy.
And the idea, I think, is in metal, the environment of the nuclei is changed by being stuffed into a very tight space, and this is analogous to the muon catalyst, in that it gets the nuclei close together, helps overcome that Coulomb barrier, that the electrostatic repulsion that's pushing them apart, by stuffing them into a metal. And maybe there is something that would increase the reaction rate above current calculations.
Right, and so and the other thing that people will, so that's a common sort of assessment of what the theoretical motivation here is, and then people will say, well, there's actually something else you need to, because if you do the calculations on that, Al, it's unobservable. Cold fusion, you would not expect it to happen. And then people say, okay, well, then there's some sort of electrons, free electrons in the metal that can sort of screen the reactions. And so for the listeners, what I mean by that is, just like in the case of the muons, the electrons can sort of, you can think about it in a very classical picture, get in between the two nuclei, and then that sort of shields some of that positive Coulomb repulsion, and get a little bit closer. But even still, that actually helps a lot, orders of magnitude. But it's still way too far off. And a lot of these theoretical papers, they calculated some of these screening effects, many body screening effects. But what they didn't look at is many body fusion reaction, or sort of that's not. They assumed a two-body fusion reaction. So essentially, they were still just assuming that the only sort of relevant picture here is looking at two particles in isolation, just like you would in a plasma. But actually, there's a lot of degrees of freedom in this condensed matter metallic environment. And so, in short, the theoretical framework that really sort of gripped me and started to paint a picture that, we've got a lot of work to do. There's no sort of accepted theory for cold fusion or Lehner, but it's starting to sort of connect some of the dots. Is instead of thinking about this as just merely some sort of collision between two particles, if instead, if you think about a pair of hydrogen as an excited state of helium, and so there's a little bit of a jump there that you're making, but I think it's sort of a reasonable jump to make. That it is in the extreme an excited state of helium. So let's take, for example, the classic sort of cold fusion fuel, deuterium, which is just a heavy hydrogen. So the nucleus is a proton and a neutron, and called for short a deuteron is the nucleus of deuterium. And sort of two deuterons is sort of like an excited state of helium-4, which is two protons, two neutrons. So we're conserving all these, the number of protons and the number of neutrons. And so in that case, in that sense, you would expect that there would be some sort of spontaneous decay rate, i.e. fusion rate, of the pair of deuterons to the helium-4. You want to reduce the potential energy, and so there would be, you'd expect there to be some decay. Now the problem still remains that decay is severely suppressed because of the Coulomb barrier.
Right.
Now the next sort of step here, and I should also mention that we describe this in a little bit more detail in our technical manuscript that we used as our in our application to ARPA-E, and we've posted that publicly on an archive for anyone who's interested to see and try and connect it with some of the experimental evidence. But basically, some of these degrees of freedoms, for example, like phonons, so oscillations of these metal nuclei, sort of would be experienced by these pairs of hydrogen as large oscillations in the local electromagnetic field. Large charged particle, or large charged nucleus oscillating back and forth. And the idea is that if these phonons throughout the volume of the lattice are coherent, sort of pulsing together, then you can start to paint a picture where there's lots of these essentially excited states of helium, pairs of deuterons, in the metal lattice that are now not independent of one another. They're talking to each other. They can transfer energy between one another. And there starts to be some sort of like a delocalization of these excited states. And just like in the case of that Nature Physics paper that I mentioned, where they used a coherent X-ray laser to coherently excite um, multiple iron-57 nuclei, and then they witnessed an acceleration of the decay beyond what you would classically expect. So too, in this case, we might expect a acceleration of the decay rate of the ensemble, of the collection of all of these deuteron pairs, all these excited states of helium. The advantage here is that the deuterium's already excited, right? Or the helium's already excited because you have these deuterons. Now, metal hydride experts will note that these deuterons don't pair up naturally, right? They occupy different sites in the lattice on their own. Another sort of funny thing here is that if you just have a very sort of a metal hydride or metal deuteride, I guess in this case, sort of in equilibrium, the deuterons in the metal are actually further away from each other than they are in D2 gas, right? So, but if you have vacancies of the metal in these metal deuterides, you have a missing metal nuclei, it's conceivable that two deuterons could sort of go into that and form a pair in that vacancy. And so the idea is that if you take a metal deuteride far out of equilibrium, you can and you stimulate coherent phonons, and there's a variety of different ways you might go about doing that. Then you might have these pockets in a metal volume where there are sufficient number of vacancies. There's lots of pairs of deuterons occupying these sites. They're coupled to one another, and you can have the acceleration of the decay or the acceleration of the fusion reaction that might overcome the Coulomb barrier, or at least get you within spitting distance. And so this starts to paint the picture of really this sort of answers or starts to paint the picture of how you could overcome the Coulomb barrier at low energies. It also starts to sort of get at why reproducibility might be such a challenge, because it's very easy to sort of lose this coherence, lose this these domains, these pockets where all the fusion react or the sort of interacting nuclei are talking to each other, and where you might get this acceleration of the decay.
And if holes in the lattice are necessary for this to happen, then you need a particular preparation of the metal to have those particular holes. And I see, the way you're describing this, it gives me a feeling similar to what I get when I look at room temperature superconductivity, where you have these delocalized quantum wave functions of the electron Cooper pairs reaching out through the solid and being mediated by the medium. Now you have really strange behavior that you wouldn't expect otherwise, until you could take into account how these things might travel through the metal without being interrupted at all. So there are definitely precedents in physics for this sort of pairing up of distant particles in a solid, because of the regularity of it and the fact that things can resonate in phase. So it's really kind of cool that this is an explanation. So, I mean, how is the research going? Have you had any successes in the lab? Are you working in the lab on, or is it mainly a theoretical research?
No, so it's an experimental program. There's experimental sort of labs being set up right now at MIT, and at our partner Ben Barrows from the U.S. Army is also working with us on this research project. And so he's had sort of laser-based LENR experiments going for about a year and a half now. And these laser-based experiments, just to sort of further illustrate what I mean by these sort of coherence effects, usually when we think about lasers and fusion, we're thinking about concentrating lots of really high energy lasers right at a specific point to supply that kinetic energy. But here, actually, there have been a variety, several, and this might be actually sort of one of the reasons why we're interested in this experiment, is because as far as reproducibility goes in this field, actually this is sort of one of the more reproducible experiments where, and it's really quite simple. You have a metal deuteride in sort of maybe a few atmosphere of pressure, and you irradiate it with a laser, low power, continuous wavelength laser, some pulse lasers, and you irradiate it for a long time, days, weeks. And there have been several folks who have then looked at under an SEM image of the scanning electron microscope of the surface of these metal deuterides, and they see really rather bizarre morphological features that weren't there prior to the experiment. They look like sort of like mini explosions, if you will, actually, on these surfaces. Mm-hmm. And then when you take EDS spectra, so energy dispersive X-ray spectroscopy, which can identify elements, you see that sort of within these craters or these micro explosion cavities, there's a whole bunch of different metals, nickel, titanium, chromium, zinc, that weren't there before, as far as we think, before the experiment. It seemed to be there after the experiment. And now, any good scientist will think, oh, well, this seems like contamination. This is probably some sort of false signal. But then if you look outside of this sort of morphological feature, you don't see any elemental signatures. Now, that's enough to get me interested. I don't think it's dispositive, but I think it's enough to get me interested that it looks to me like maybe, and I should also mention that these anomalous elements seem to look like fission pairs of, in this case, palladium, which is one of the sort of common metals used sort of for metal hydrides and metal deuterides. They seem to sort of pair up quite nicely, actually, as fission pairs or fission daughter products of palladium. And again, it's not dispositive, but one of the things my main sort of contribution to the research effort is isotopic analysis. And the reason why that's important is because metals, sort of here on Earth, they have a natural isotopic ratio. So elements are indexed by the number of protons in their nucleus, but elements can have a variety of different numbers of neutrons, different isotopes. And the distribution, whether you're in the US or in the UK or in Chile or wherever you are, will have the same, more or less, barring some sort of geological processes that take a long time, more or less the same isotopic distribution, the same frequency of different isotopes.
Right.
But if a palladium nuclei in one of these samples was fissioning, then you would expect that these elemental signatures, these elements, these anomalies, would have a natural isotopic distributions. And so that's part of the reason why sort of we're really interested in a variety of different isotopic analyses, partnering with, sort of very, institutions that have been doing these analyses, for decades, to try and sort of probe these anomalies. But so these are some of the sort of types of experiments that we're interested in, and the types of quality of data that we're interested in collecting to really sort of paint a more comprehensive picture. Either this is contamination or it's potentially a nuclear anomaly, and we want to sort of figure that out.
No, I certainly applaud the efforts to put some of this data on a more stable footing with some good reproducible analyses. It certainly is important to getting to the root of some of these anomalous results, because definitely that's one thing that I think most scientists would agree on today, is that there are anomalous, unexplained results that seem to continue to be popping up, and more reputable labs have been doing some good studies on this, showing that there are still things that they can't explain happening. No one has yet been able to harness a reproducible reaction in a scientific paper. There are companies that are trying to commercialize cold fusion-based heaters that purport to deliver more heat energy than they take from the grid. But I haven't seen any good studies or reviews proving that fact. This field does attract snake oil salesmen, and they certainly would glom on to buzzwords like cold fusion. Do you know anything about the commercialization efforts of cold fusion? Or is it real, or is it a scam? Or
yeah, so I know some of the people involved in some of the companies. My perspective on this is my theory of change here is that if there's really something here, then there will be a nuclear anomaly that needs to be published, and it needs to be published with very rigorous scientific standards in a mainstream peer-reviewed publication. And I think my strong suspicion is that if and when that anomaly happens, gets characterized, and gets written up in a paper, if that happens, I think you'll see sort of the floodgates open, and a lot of research groups that you never thought had any interest in cold fusion, and maybe they didn't, we'll start working on this. And that's ultimately what we need. We need a lot of scientific labs working on this. I try not to pay much attention to commercialization efforts, which doesn't mean that they're all sort of snake oil salesmen. Some certainly are. But I think even if there are some people who think they're doing good work, could be seeing results that are actually the product of poor calibration, poor controls. There's really nothing there. They could also be seeing some anomalous effects themselves. I think I try not to spend my time in that arena, because I think the most important thing is there are good labs working on this. There's rigorous scientists that are working on this. Although I would just say that I think actually the vast majority of this in the scientific community would be unaware or surprised at the fact that there are good labs, good scientists working on this. And I think that they would also be, except for some of these sort of like older folks in the physics or chemistry community who maybe had heard that there were reports of neutron bursts from reputable labs in the early 90s. But most people, I think, would probably just associate cold fusion with a unreproducible report of excess heat by Fleischmann and Pons, and that's it, and no one saw anything else after that.
That's true. I mean, that is the prevailing view, I think, for people who haven't looked into it. And to a certain extent, the longer any of these companies go without providing a Nobel Prize-winning paper, the more skeptical I become of their efforts, because, let's face it, some people just want to make money without actually doing the work. So there are a lot of that out there. We've seen companies, faking it till they make money.
For sure.
There was, as I alluded to earlier, the recent announcement of room temperature superconductivity from researchers in South Korea, and they released their work on the arXiv preprint server. So this is a online server where you can release unreviewed research for the community to digest. And it was a huge announcement, and they got lots of press coverage around the world, because obviously room temperature superconductivity is another one of these holy grails that if it happens, you're getting a Nobel Prize and you're changing the world. But it was subsequently found to be irreproducible, but it doesn't seem to have stirred up the same fervor of stigma that the Pons and Fleischmann announcement got back in '89. Do you think that the scientific establishment has learned a lesson from this? Do you think we're more accepting, or are we still in the same boat?
No, I don't think so. Actually, I think that there are sort of real problems within science as it pertains to sort of dealing with anomalous phenomena that are just sort of beyond the pale of sort of maybe the current paradigm that struggle with reproducibility challenges. Again, I think in some cases, challenges with reproducibility are because we don't have a theoretical understanding of the phenomena at hand. I mean, I'm not a superconductivity expert, but I think like maybe the best sort of tweet that I saw in the fervor was I'm forgetting his name, but I think he's a XRD specialist at either Oxford or Harwell. I don't quite remember, in the UK. And he had a tweet where he was basically like looking at the XRD pattern that they had published.
That's X-ray diffraction.
Yes, thank you. Sorry. And sort of it's an analysis, a tool that can sort of tell you about the structure of the crystal lattice. And he basically was saying that he doesn't think that he didn't think that the XRD pattern was very good. And if the XRD pattern is not very good, then you might not really know what, if there is some sort of room temperature superconductor effect, and then at the time nobody really knew, and I think still there's some sort of question marks, although I haven't followed it very carefully. You might not even know what the material that you're going for actually is. And so I think that was sort of like the most brilliant tweet, because it was just sort of like, solid state physics is really messy, super challenging, really hard to reproduce results, even when you have the XRD pattern. And then if you don't have the XRD pattern, then it's really hard. But I think that there were some sort of people who, like, 3 days or 4 days or whatever after those preprints were published, were just sort of totally nasty, uncollegial, the paper wasn't written well. Maybe it's because English isn't their first language. But I mean, there were problems, with like the y-axis of one of their figures was not the right. The scale made it so that you couldn't really see if there was if current if resistance or resistivity fell to zero or not, because the slope looks like it's zero, but maybe it's not zero. So there's a number of challenges like this, and there were sort of genuine critiques to make of the preprints, and maybe even putting them in as preprints wasn't the right move. And I think actually one of the preprints was posted without the other co-authors' approval and acknowledged, or they didn't know about it. So I think there's a number of problems with how that whole situation unfolded. But no, I think that there is sort of a fundamental conservatism in science. And I think the other thing is it's sort of, I imagine it's quite difficult to know that you're being overly conservative as a community, or sort of, there's some sort of like performative skepticism. Again, I think sort of like there are people in the cold fusion community that are deeply skeptical. Some of the folks I spoke to on the Google project, or were affiliated with the Google project, deeply skeptical, but not dismissive. Very intentional about doing really good work in that community, trying to reproduce results, trying to find results that appear to be anomalous but actually have prosaic explanations. So I really appreciate that sort of healthy skepticism. I think there is a sort of social currency that you can gain in the scientific community by being sort of performatively skeptical or overly cynical. And I think that's really deeply unhealthy, and I don't really know what the solution to something like that is, but I think it's a deep cultural problem.
Egos are still present in scientific discourse, and egos get pushed out of joint. I do like the way that science is self-correcting, in that eventually experimental data will drive the community, but that gets delayed when leading thought leaders in the community have their egos out of joint. And I think that has held back this field for a long time, and certainly it's present in just about every field. There are senior scientists whose word is taken as law, and if they say something is not going to work, then it dissuades other people from working on it. And these people are sitting on the grant review committees as senior scientists. So junior scientists know not to be presenting abstracts or proposals that counter their views. So there is a human element to the science that can slow the progress, I think. And so I think we have to be very aware of how egos can become involved, and to take them out of the process if at all possible.
Couldn't have said it better myself.
So this is great to learn about your investigations. When should we expect to hear results and papers published on these anomalous LENR or cold fusion effects?
Yeah, obviously, the research program, we got awarded in March, but it only sort of first kicked off a few weeks ago. So, and I think all I think we can say at this point is that we are committed to doing really good, rigorous science, characterizing relentlessly all of our conditions. And if we, the other thing that I say is we're committed to publishing regardless of what the results are. So, if we don't see any anomalies, then it doesn't mean that the Leonard field has been disproven, or but what it does mean is that because we're so committed to sort of very carefully characterizing the structure of the materials, the conditions within the materials that we're inducing, which is very tough business, but because we're so committed to that, hopefully the idea is that we can at least identify a region of the very vast parameter space where we don't think any anomalies exist. And I think that that's an important scientific contribution, whether or not we see any sort of Leonard nuclear anomalies or not, trying to bring sort of really good characterization, trying to sort of either say there looks to be something here, or we've really carefully, analyzed this parameter space, and we don't think that there's any anomalous activity going on.
Well, best of luck on your investigations and best of luck on your PhD work as well. Thank you for coming and chatting with us today. For spending your time, I'll fire you a T-shirt from the Rational Review.
Well, thanks, Al. I'm a big fan of the podcast. I think you do great stuff, and I think I think I probably speak on behalf of a lot of others in the learner community that we thank you for sort of taking an interest in our field.
Oh, thanks for coming on. Send me some references to chat with on future podcasts. I appreciate that.
Will do.
Thank you.
If you'd like to follow up with more in-depth discussions, please come find us on Facebook at The Rational View and join our discussion group. If you like what you're hearing, please consider visiting my Patreon page at patreon.podbean.com/TheRationalView. Thanks for listening.